Okay, another way to look at relations between functions, or just relations in general, is to look at them what we call parametrically. Okay. All right, and ultimately, what we're going to have, instead of an equation that has y and x, like for instance, one of our 12 is y equals x squared. Okay, this is a direct relationship between y and x. Okay, sometimes we're going to be given a relationship that's in terms of a third variable, which we call a parameter. We usually call it t. It doesn't necessarily have to be t, but that's what we generally use here. A lot of the applications that we do with parametric equations are where x and y are dependent upon time. And I don't know if that's why they chose t, but that's probably pretty likely. Okay, so what it's going to look like is something like this. Instead of giving an equation, one equation that has x and y in it, okay, we're going to be given two equations, okay, one for x and one for y, both in terms of t. So ultimately, the x and y on the coordinate plane, if we were to graph this, we'd still get a location. Okay, but the location of the whatever we're talking about is going to depend on what t is. And like I said, in most cases, the t is going to represent time. So if we said that, if we just said that t did represent time, and we want to know where is this object, let's say, we've got some moving object. Okay, where is it when time is 5? Okay, whether time is in seconds or hours or days or whatever, it doesn't really matter. But if I want to know where it is at time 5, or at any of these points given down here, all I need to do is plug in the time and figure out what the coordinates are. So when I make a chart for something like this, I would make essentially, instead of an XY chart, it's going to be a TXY chart. Okay. So for my particular example, I said I want to know where this object is at time 5. Okay, I'm going to plug a 5 in for x, or into the x equation, so I'm going to do 5 minus 1, which is 4. And then if I put a 5 in here, I'm going to get 25 plus 2, which would be 27. And then when I graph this relation, okay, I'm going to go ahead and plot the point 4, 27. Okay, so somewhere on the coordinate plane, I'm going to find 4, 27, I'm going to plot it. If I were to do the same thing with these other points, I'm not going to do all of them, but if I did negative 3, let's say, if I put negative 3 in here, I'm going to get negative 4. If I put negative 3 in here, I'm going to get 9 plus 2, which is 11. If I put, let's say, 0 in there, I'm going to get 0 minus 1, that's negative 1. If I put 0 in here, I'm going to get 0 plus 2, which is 2. And I'm going to put 2 in there. Again, I'm just picking some points out of here instead of doing the whole entire chart. But ultimately, 2 minus 1 is going to give me 1. And then if I do 2 in here, 2 squared is 4. 4 plus 2 is 6. So again, are we going to actually graph these points? No. Okay, these are the parameters. Okay, we're going to graph on the xy plane, just like normal. We're going to graph the point 4, 27, negative 4, 11, negative 1, 2, 1, 6, and so on. And ultimately, that's going to give us a graph of something. Okay, we may or may not be able to recognize what the graph is by the equations given, but when we plot these points, okay, the graph may look familiar. Okay, it may look like one of the graphs that we already know, or some variation of it. Okay. All right. So looking at the rest of the table, they actually made the rest of the table for us over here on this slide. Okay, and again, they wrote them down as ordered pairs. And then what we'd want to do with those ordered pairs is draw them. Okay, we want to plot these points and see what it looks like. Now, here's a bit of good news, is that your calculator has a parametric mode. So under your mode button, which is on top up here, if you go down to the 4th line and put it on PAR, which stands for parametric, okay, you can graph a set of parametric equations, okay, with your calculator. And once you put it in parametric mode, if you go to y equals, okay, you'll notice that it gives you x of t, y of t. So it changes the whole y equals part around so that you can actually type in 2 equations, because that's what you need when we're dealing with parametric equations. And in our case with the first one, we'll say x minus 1, and you'll notice that it even changes the variable to a t instead of the normal x it uses. Okay. And the other one, we have t squared plus 2. Questions so far? Okay, this would be a lot easier to pay attention to and stay up with if you actually got your calculator out and followed along and did this too. So if we want to see the graph that this produces, and again, we could plot these points by hand on a coordinate plane too, but if we want to do it quicker, essentially, the other key issue, just like all of our graphs, is we need to make sure the window is good. So let's look at our window here. I'm going to go back to the t's in just a minute here, but if we look at our x and y windows, we have, in the x direction on the points that we have -4 over to 2. So right now I have it on -10 to 10. That's fine. And then in the y direction I have -10 to 300. So I'm going to change that to 10. Okay. You'll notice that we do have an 11 point here. So maybe I'll make it 15 so we can at least see those 2 points on the ends, if you will. Now going back up to the t's here. Okay. When we have a t min and a t max, very similar to x min and x max. Okay, we're going to want to use this as our guide in order to put our t min and t max in. Right now I have it at 0. So we wouldn't see these points over here because t is going to start at 0, but we don't want to start at 0, we want to start at -3. So let's go ahead and put -3 in there, and then we'll go to 3 here. And then the t-step, this should be the default, this should be this number in your default. Okay. As soon as you hit that, that's what you should see. Don't change that, there's really no good reason to. But if it is different than that, go ahead and change it right now to this. Just use that approximation right there. Okay.
What if we have to type in, like, what if it's like find the points like -3, -1, like, would we just leave it like -3, 3?
Still want to have a range that's going to include all the t's that you put in. Okay. Yeah, so just make sure whatever you put here includes all the t's that you put in to create your points that you did. Okay. All right. Good questions. What else? All right, well, let's see the result then if we hit graph. Okay. Looks like a parabola, doesn't it? Okay. Now, one thing that you'll notice here is that it stops, okay, which is not too surprising because we told it only to use t values from -3 to 3. Okay. If we made our t values bigger, which we could certainly do, we can put other numbers in there besides -3 to 3. We could put -5 trillion in there if we wanted to. Okay, so ultimately, if we made the t-step bigger, for the t min, t max, I should say, if we made this bigger, like if we went -10 to 10, okay, ultimately that would produce more of the parabola. Fair enough? Okay. So we can make that really however we want it to look. But if we just close it off between -3 and 3, those are the only numbers that we can put in there. Therefore, it's going to only give us part of what that graph would look like if we were to use any t possible. Okay. All right. Now, the other thing I want to show you too with the calculator is that if you look at your table at this point, I'm going to go to table set first. It is on ask. Okay, I'm going to put it on auto because I want it to produce just a table for me, just a list without me having to type stuff in. I'm going to put my change in table on ones, okay, and then my table start, I'm going to start at -3. Okay. And then from there I'm going to hit table. And you notice that it does exactly what I have on this paper here. It gives me a list. Okay, starts at -3, and keep in mind that that -3 we put in there was for t's. Okay, so and remember with an auto situation, it's going to give us as many as we want here. We can just scroll up and scroll down and see whatever t value we want to. It's going to give us a point for anything we want, but ultimately it just mirrors that table that I have written here. Okay. So that's also convenient because if we have parametric equations, we can produce that table rather quickly as well. Okay, we don't have to do it all by hand. Okay, the table is right there for us if we put it into x and y equals. Okay. All right, questions so far? All right. Okay. The other skill that we need to be able to do with parametric equations is we need to be able to go from the parametric equations to an equation that has just y and x in it. Okay? Because ultimately our conjecture at this point is, wow, that, looking at the graph, okay, that produces a parabola. Fair enough? Okay, so the question is, algebraically, is there a way that we can prove that it's a parabola? Okay, and the answer in some cases, not all, in the cases that we're going to look at, it's going to be a yes, but ultimately what we want to try to do is show that that set of parametric equations is actually equivalent to some equation in xy. Now remember, if it is, okay, we're expecting what's going to happen is that we're going to get an equation that has y equals and then something x squared. True? Because we're expecting to get a parabola here. So knowing that what we're setting out to find, okay, might be helpful. But bottom line is we need to go from one equation to two equations to one equation, and we also need to go from 3 variables to 2 variables. Okay, we need to get rid of t is what it boils down to. So what we're going to do is, just like when we solve systems of equations in algebra and algebra 2, okay, we need to somehow combine these equations, okay, and get it so that the t is gone. Okay. So we have two options. If you remember when we solved systems of equations, okay, one option was to use substitution. Okay, so we have a substitution option, okay, or we have an elimination option. And which one we use is really, it's up to us. Okay, we could use either one. Okay. Now in this particular case, again, keep in mind what we want to do is get rid of t. Keep that in mind. So if we have x equals t minus 1, this would be a pretty easy equation to solve for t. True? And then ultimately, what could we do with that stuff? Okay. We could substitute it into the y equation for the other t. True? So if we did that in this case, our new equation for y would be x plus 1 all squared plus 2. And what have I done here now? I set out to get rid of t, and what did I just do? I got rid of t. I got one equation that has two variables instead of two equations that has three. Okay. And if I expand this, if I write x plus 1 times x plus 1, and I FOIL that, then my final answer here is y equals x squared plus 2x plus what? Plus 4. Oh, sorry, you're right. Sorry, plus 3, I should say. Thank you. So ultimately, if I expand that and then add 2 to it, I get a final answer of y equals x squared plus 2x plus 3, which is ultimately exactly what we thought is a parabola. It's a quadratic equation. Okay. And just to double check, keeping in mind what this looks like on that window, if we go to our mode again and put it back into function mode and type that equation in, x squared plus 2x plus 3, and graph it. Alright. We hopefully, if we did it right, we'll see the same picture. Okay. Alright. Questions so far? Alright. Let's take a look at another set of parametric equations. If I were to be given x equals, let's say, 2t plus 1, and y equals 3t minus 4. Okay. Let's first take a look at what that looks like graphically. If I put my calculator back in parametric mode, and I do my 2t minus 1, my 3t plus 4. Oh, you're right. If I could read my own writing, that would be helpful. Alright, and I'm going to do my, I'm going to keep my window the same. I'm just going to use -3 to 3 here. Again, keep in mind I'm only going to see a portion of the graph if I do that, but hopefully it'll be enough of the graph to see maybe what this general shape is. Okay. And looks like a line. Okay. Keep in mind it's a segment though, because we're only using -3 to 3 with our points that we're plotting. Okay. And so we have reason to believe at this point, okay, that this produces a line. Okay. And well, remember what your calculator is doing as it graphs this is it's just plotting points. Okay? And it's plotting points on the t-step. It's plotting a point every 0.13. If we made the t-step smaller, like if we did 0.001 for the t-step, it'd plot a way more points, but it would take a lot more time. So you can put it on a smaller t-step if you want, but you'll have to wait because it's going to take a while to plot that many points. Okay? So this t-step usually is the default, like I said, and it usually gives you a reasonable picture of the graph. Okay, but that's what it's doing is it's plotting points. Okay, all right. So the question is next then, if I think that this is a line, how do I prove it's a line? Well, okay, I get rid of the parameter. I write this into one equation that has just y and x. I get rid of t, in other words. Now you got two options here. If you want to get rid of t in this case, you could substitute again like we did in the last one. You could solve this for t or solve this for t for that matter, and then substitute. Okay, I would conjecture though that this one is easier to get rid of t by using elimination. Okay, so what I would do is I would multiply the top equation by -3, okay, and the bottom equation by 2. Okay, because ultimately what did that do for me in the t column here? Okay, if I were to add these right now, what's going to happen with my t's? They're going to cancel out. So if I multiply that one by 2 and that one by negative 3, okay, I could get rid of those t's and I would have negative 3x plus 2y equals negative 11. And again, this is exactly the same thing that we did with the elimination process when we solved systems of equations with two variables. Okay, so we're just setting it up so that when we add column by column, okay, we get the t's to be gone. And that's the whole point, is to get the t's gone. Now again, on this column, of course, these are not like terms, so we can't do anything with them other than write a plus sign between them. The negative 3 and the 8 are like terms. We can put those together. Okay, and recognize at this point that it's the standard form equation for a line, just like we expected. Okay, if you want to, you could write this into slope-intercept form. Okay, you get y equals 3 halves x minus 11 halves. Okay, and so this would be, again, verification that what we saw, in fact, was the line with a slope of 3 halves and a y-intercept of negative 11 halves. Okay. Questions so far?